So you have now done ionic bonding, which was our first type of bond that you can get between atoms. And now we're going to move on to covalent bonding. So in covalent bonding, it's also an intramolecular bond. Remember we said that is bonds that occur between atoms. So if you look, we're still just busy looking at bonds between atoms. And in a covalent bond, we are going to form a molecule. So that's why you'll see the definition says an intramolecular bond is this bond that occurs between atoms, and there's the A, intramolecular bond. So it's the bond between atoms within a molecule. And a covalent bond is not going to be a transfer of electrons like you saw in ionic bonding. This time the one atom is not strong enough to take the electron totally for itself. So what they're going to end up doing is they are going to share these electrons. So it's going to be a sharing of electrons. And we're going to look in detail at how that happens. I'm actually using the notes so that you can see where in the notes we are. So I'm hoping that helped you a little bit. So if you look at the covalent bonds here. So, oh man, I did not want to draw that line. So if you look at carbon here has 4 valence electrons. You know already how to draw that. So you've got your valence electron there, valence electron there, valence electron there, valence electron there. Sorry, I am still coughing. But those electrons still want to share, or still want to be a full part of a full electronic structure. So now this time the hydrogen is not going to give these electrons are not going to be given to carbon. All that's going to happen is that the orbital in which they are a part of, in which they are moving, the orbital of the carbon and the orbital of the hydrogen there will overlap. And these 2 orbitals will overlap, and these 2 orbitals will overlap. So carbon ends up sharing 4 electrons with the 4 different hydrogens. Please remember all molecules are in 3 dimensions. We can only draw it on a flat piece of paper, but we try sometimes to show you in 3 dimensions, and that is what this one here is trying to show you. You could have also just drawn it with the carbon. Now here you see the orbitals overlapping. So in this one you can now see the orbitals overlapping. This is called a Lewis structure like you are used to. But we're also going to make our life a little bit simpler. Sometimes we're just going to draw one line to show the bonding pair of electrons. So the lines are there to show that there's a hydrogen sharing an electron with carbon here. And that line actually represents the hydrogen's electron as well as the carbon's electron. So there's 2 electrons for each line. So that you know the difference between a Lewis structure and a Cooper structure. So now if I take that away, you need to be able to show how these bonds form. So again, hydrogen, very easy. If I have one hydrogen with its 1 electron there and another hydrogen with another electron there, what happens is that those 2 orbitals again will overlap. So you can show the orbitals if you want overlapping there, but it's going to form a hydrogen bond between 2 atoms, which is then sharing the electrons, and they end up having a full electron structure by sharing. So if we go back to the previous one, and what I mean by the full electron structure, if we look here with the carbon ends up having now 1, 2, 3, 4, 5, 6, 7, 8. So the carbon ends up with 8 electrons in its outside energy level. And remember, from bonding, that's what carbon wants, because it wants to be as close as the closest noble gas. It wants to be the closest noble gas. So it wants 8 electrons in its outer energy level. But if you look at hydrogen, the hydrogens now end up with electrons with 2 happy as well, because they have 2 electrons, 2 electrons, 2 electrons, and 2 electrons. So the hydrogens end up with 2, and you know that hydrogen is in energy level number 1, so therefore or period number 1 and only 1 energy level, so they only need the 2 electrons. So in the ionic bonding, electrons were transferred so that atoms could get full electronic structures. Here in covalent bonding, the big difference is that electrons are being shared to get a full electron structure. And that's as simple as covalent bonding is, but we're going to have to practice a few of these. So if you look on page 214, there's an example done for you here at the bottom that you can already see. I keep on drawing lines on this page. There's the example. So the one hydrogen's atom electron there and the other hydrogen's electron there, gets shared by the 2 hydrogens because those 2 orbitals overlap. I think you're getting the idea. We just, again, what Cooper structure is, that just means it's a line, but each line actually represents 2 electrons. So remember, it's the shared pair of electrons. So it's 2 electrons that they represent. They're the shared pair of electrons. Now, it's not always only 1 pair of electrons being shared. If you look at nitrogen here, nitrogen had the 2 lone electrons there. We call them a lone pair because they're already paired up, and there's another lone pair. But if you look at nitrogen, the one nitrogen atom has, I need another color, the one nitrogen atom, these 2 electrons here can share. These 2 electrons here can be shared, and these 2 electrons here can be shared. So those orbitals will overlap, which means that nitrogen actually will be sharing 3 pairs of electrons. And that is why when you saw nitrogen, there's 3 pairs of electrons being shared. It is nice if you show them in different colors like we normally do. So this nitrogen will draw this nitrogen's electrons in blue, and then we'll draw the other nitrogen's electrons in another color so that people can see that you know which electrons belongs to which nitrogen. But those electrons in the middle then are being shared because these orbitals here are overlapping. So now you just need to practice drawing the Lewis structure for different for different molecules. And I'm going to do exercise for the first 2 with you, and then I want you to really pause and do the rest yourself, and then we can go through them again after. So please, like I say, pause and do them first, because it does tell you to do the exercise on page 215 and 217 and then mark them. So pause this video and do the exercise, or I'm going to do the first 2 and then you can pause it and do the rest. So if you look at the Lewis structure, drawing lines again, of chlorine gas, you know from a long time ago is Cl2. But now we're going to see, is that actually what's going to happen? So what you're going to do is you're going to draw a Cl, and if you look at the periodic table, you will see chlorine has 7 electrons. So 1, 2, 3, 4, 5, 6, 7 electrons. So there's an electron able to share there. You'll see later on when you get a bit more used to drawing these, we normally draw the alone ones in the middle so that we can easily see where they are sharing. Another chlorine atom will look like this as well. So we've got 1, 2, 3, 4, 5, 6, 7. So they will obviously look exactly the same. But now if you look carefully, you can see that there's a lone electron here. Oh, I'm still wiping it out. There's a lone electron here that could be shared with a lone electron there. And I shouldn't call it unlone, it's an unpaired electron. And those orbitals can now overlap. So I'm sure you're able to see that it would have been much easier for me to not draw it like that, but rather say that Cl has its own 7 electrons. I'm just going to quickly redraw it. And then the other Cl has its 7 electrons, and we draw the ones that are not paired up in the middle, because then you can nicely see that these two orbitals here are now going to overlap, and that gives us the formula for Cl, for chlorine, that you already know is Cl2. So you can now prove that that formula is Cl2. The next one is hydrogen chloride. Hydrogen chloride, we're going to follow the same procedure. We're going to say hydrogen has 1 electron, and they said chloride, so it's a chlorine again. So there's my chlorine with its 1, 2, 3, 4, 5, 6, 7 electrons. And again, you can see here those orbitals are going to overlap, so that those electrons can become my shared pair, and my formula will then become HCl. Because now, if you look at both these atoms, the chlorines at the top each have their electrons that they wanted, so they each have 1, 2, 3, 4, 5, 6, 7, 8, because it's sharing that one. And the other chlorine has 1, 2, 3, 4, 5, 6, 7, 8, because it's sharing that one as well. So they end up with full electron structures. The hydrogen here gets 2 because it's sharing here, and it only wants 2. And if you look at the chlorine, it's the same as the one above, it now has 8. So if you were looking at those two first before you do the rest, please pause and then go do the rest, and then come and mark with me afterwards. I'm going ahead with water. You know the formula for water already, but like I said, you're going to prove that now. So if you look at water, we've got oxygen and hydrogen. So I'm going to do the oxygen in the middle first. So we're going to have an oxygen with 1, 2, 3, 4, 5, 6 valence electrons. So now you should be able to see that this electron as well as this electron can still share its orbital with another element. And if I look at hydrogen, hydrogen only has 1, remember? So if hydrogen has only 1 electron to share, that means this part is happy because it's got an electron to share. But now what about the other poor electron at the bottom of the oxygen there? And that is why I then need another hydrogen to come in here, and another hydrogen will then bond there to form H2O, because now this pair is also happy because it's sharing. And if you go and count all the electrons around oxygen, we've now got 1, 2, 3, 4, 5, 6, 7, 8, because we count the ones that they are sharing, and the hydrogens end up with their 2 electrons again. The formula for water, I hope you all know, is then just H2O, because I have the 2 hydrogens sharing with the 1 oxygen. I'm just going to take this molecule away. I'm hoping that you've marked it. I can quickly write it in there so that you know it's an O with, they wanted the Lewis structure, so I can't really now go and do a Cooper structure. It would be easier to just draw a Cooper structure, but you've got 1, 2, 3, 4, 5 with a hydrogen and another hydrogen, just to make space at the bottom there. Happy with that one. Now I'm going to do oxygen gas. I'm going to go a little bit faster because I think you're kind of getting the idea. So for oxygen, I have an O with 1, 2, 3, 4, 5, 6 electrons. And then I have another O with 1, 2, 3, 4, 5, 6 electrons. On purpose, I left the electrons that you can see how they are sharing. So you can see these two here will share. These two here will share because they are unpaired electrons. And now I've got 2 electron pairs being shared. So they give me the oxygen molecule. And I think all of you know that as well, because there's now just 2 of them. This formula is just going to be O2. Moving to the next one, they want ammonia with nitrogen and hydrogen. Ammonia is one of the formulae you'll learn, and it's also in that table as ammonium, but that's NH4+. So ammonia is NH3. It's actually easier if you know the formula to go to the structure, because if I know it's NH3, I already know it's going to be 1 nitrogen sharing with 3 hydrogens. So if we're going to prove this with the Lewis structure. So if I look at hydrogen we know already only has 1 electron to share. But nitrogen has 1, that's very big, I'm going to use a small dot, has 1, 2, 3, 4, 5 electrons. So you should be able to see that this here we can have this is a pair that could be sharing there. But now only one of those electrons that were alone is happy. So we need to make sure that the others also become shared or become happy. So I'm going to have another hydrogen with its 1 electron sharing there, and I'm going to have another hydrogen with its 1 electron sharing there. And this is then the orbital that's overlapping. These orbitals are overlapping, so you get an NH3 molecule. I hope you are seeing how these help us to predict the formula for the molecule. Then carbon dioxide is the next one. Carbon dioxide is an element that you also know the formula for. So we can draw it, but we can put it in here already. But we're also going to use our structure and see if it actually leads us to that. So if I look at carbon has 4 valence electrons. 1, 2, 3, 4. Then oxygen has, according to the periodic table, 1, 2, 3, 4, 5, 6. So if I look at only this oxygen, then you can see that there's a pair that can share, and there's a pair that can share. So my oxygen on the left-hand side becomes happy because it's got a full 8 in its outside energy level, but the carbon still has the 2 lone electrons. So that means I need another oxygen. So I need another oxygen also with its own electrons. So here I'm going to have 1, 2, 3, 4. And because the bottom one is shared already, I'm going to do the top one, but it doesn't matter if your lines cross each other. So here I can then see there's another pair of electrons that could share there, and there's another pair of electrons that could share there. So a Cooper structure for this would be much easier, because all you would do is you will draw your carbon, showing that 2 pairs are being shared with the 1 oxygen, and 2 pairs are shared on the other side with the other oxygen. So this will be our Cooper structure, but like we said, in this table they asked you for the Lewis structure, so for now we're just going to stick to the Lewis structure. Okay, get rid of that. And that was CO2. The last one that they give you is hydrogen cyanide. Now the cyanide ion is one of the ions in the table that you should have learned by now, is a Cn- ion. So but that also tells you that it contains hydrogen, carbon and nitrogen. So let's see if we can get the formula now. If I look at nitrogen, nitrogen has 1, 2, 3, 4, 5 electrons. So there are 3 there able to share with something else. They told us that we've got cyanide, and we know that the CN, if we look at carbon, if we look at carbon, carbon has 1, 2, 3, 4. So now there's a bit of a problem because we also have a hydrogen, and the hydrogen only has 1. Now we need to think, how are these things going to share? So if hydrogen shares there with the 1 pair there, then you can see that nitrogen can share there and there, and now this is going to become a very weird drawing, there. So I'm definitely going to have to redraw this a little bit better. But then once you've done that, you can always, we will give you marks for that because it is actually showing what is happening. But now you know that we can draw it a bit neater. So what you can do is the carbon is the one that forms the most bonds. So that's almost a rule of thumb. You can draw the one that forms has the most lone electrons. So we know carbon had 4. So carbon had 4. And nitrogen could share 3. So nitrogen we'll draw here, and we'll say nitrogen has 1, 2, 3, 4, 5 electrons. And then we've got hydrogen that has only 1 electron. And now we can show much better. So there are the orbitals sharing, there, and then there we have the other one. So the name or the formula, chemical formula for the substance will just be H, because the positive one always comes first, and then Cn. And that's your formula. So that's the whole of exercise 4 done. Now once we have these bonds, remember I said it's a bond only between 2 atoms at a time. We're not only happy with you telling us that it's a covalent bond. You're going to have to classify our covalent bonds as either polar covalent or non-polar covalent. And to do that, you need to go back to electronegativity again. And remember what I said, electronegativity is how badly an atom wants those electrons that they are sharing. So sometimes they're going to share them evenly. If they share them evenly, then we have a pure or a non-polar covalent bond. If they do not share them evenly, then we have a polar covalent bond. So I want to explain that to you a little bit quickly. So we need to look at the periodic table that I hopefully have here. Let's just find one, yes. So if you need to have your periodic table next to you again for this. So I love drawing lines over the paper. So I'm just going to find an empty spot here for us to write. And now what we're going to do is we're going to look fine. If I have a hydrogen sharing a pair of electrons with another hydrogen, so this one we've done already, we know each of them has 1. Now your next step is to go and look at the electronegativity. If you look at the electronegativity for hydrogen, this one has an electronegativity of 2.1, and this one has an electronegativity of 2.1. So remember, electronegativity is the tendency of an atom to attract those electron pairs. So it's how badly these atoms want these electrons. So this electron pair that's being shared in the middle is being pulled towards the right, to the left by that hydrogen with a force of 2.1, and it's pulled towards this side to the right with a force of 2.1. So neither one of those are winning. So if the electronegativity is equal, like you have it here, equal electronegativities, then we have a non-polar covalent bond. Please say the whole thing. You have to say non-polar, covalent, and bond, because a bond is between the two atoms. Now, if they were not hydrogen, so if they were something else, so moving across to another empty space, let's say if were not the same, it's not necessarily the same, but let's look at hydrogen, and let's say hydrogen is combining with chlorine this time. So you know hydrogen has 1 electron, chlorine has 7. So 1, 2, 3, 4, 5, 6, 7 electrons. You can see that this pair here will be shared. Okay, I went a little bit faster because that part I think you're fine with. So now we go and look to decide if it's a polar or a non-polar covalent bond. We have to look at the electronegativities, and like you saw before, hydrogen is 2.1, and chlorine, if you look at the electronegativity of chlorine, it's 3. So this time, those electrons are being pulled a little bit towards the hydrogen because they with a force of 2.1, but they're being pulled a lot towards the chlorine with a force of 3. So as soon as there's a difference in electronegativity, so we say different, we use difference as a triangle. So as soon as there is a difference in electronegativity, in this case the difference is 3 minus 2.1, which is 0.9. If there's a difference, then we know that the electrons are not being shared evenly. So the electrons are living more on the chlorine side, and therefore this is then a polar covalent bond. And as I said before, you have to write the whole thing out. Polar covalent bond. So there you go. So to decide if it's a polar covalent bond or a non-polar covalent bond, basically you have to look at the electronegativity. If there's a difference in the electronegativity, like there was here, then we know it is a polar covalent bond. If there is no difference in the electronegativity, then it's a non-polar covalent bond. I do think you are ready to go and practice this, and I'm not going to do this exercise for you right now, so but I'll post the answer. Exercise 5 on page 217, you need to go and look at those molecules that are given to you and decide if the bonds are polar or non-polar. Bye-bye.